where we perform the quantitation based on the MS1 data in combination with an identification on the MS2 data. Then we looked at the quantifiable proteins from the 3 different instruments, and we looked at if all those numbers here would tell us stories, and they tell us a bit of a story. They tell us a bit about what's going on. Well, one thing that is sort of a bit comforting is that there is a big overlap between the 3 different instruments. Well, it should be if it's the same sample we're looking at. It would be very disappointing if that would be even smaller than this. The other thing that we notice is that there is a particularly big overlap between these 2 samples here, this one here and that one, where you have really excellent agreement, and there is less of an overlap between these 2 samples here or between those 2 samples. This sample here has by far the largest number of what it claims are quantifiable proteins, and just to give you names to the different instruments and the different approaches, this one here is the Thermo-QX active. This one here is a SciEx instrument where we've done swath, so it's a triple TOF. And this one here is a Waters where we've done MS2V. Now, one conclusion that one could draw from this is to say, well, obviously Waters instruments are clearly the best one of all of it. Unfortunately, it's not that straightforward because some of this, like, there's other factors that influence the whole thing as the acquisition approaches are so different. Database searching is done in very different ways, and although false discovery rates can be calculated for all 3 different approaches, it's not that straightforward to even compare them afterwards. And I think that in this here there is still a large set of proteins hidden that were not even in the sample. A nice thing about all 3 experiments is the speed at which they were carried out. The Waters experiments, which sort of yielded, according to their software, about over 3,000 quantifiable proteins per run, was 90-minute HPLC runs. Whereas on the triple TOF and on the QX active, it was 2-hour runs, which is still very fast for the number of proteins that were identified in a very difficult sample with a high dynamic range. So one lesson that we also learned from this graph here is we're getting actually excellent data from all 3 instruments. This is actually going to be the last slide that I'm going to show you. That's data that are taken, basically clobbered that together overnight after I arrived here this morning. This is data from the triple TOF, the swath approach, as a heat map, and that is actually quite encouraging as far as the analysis of our data goes. Just to help you a bit with reading the heat map, here on the, every vertical line here corresponds to a particular protein, and every horizontal block corresponds to one of the samples. Altogether, we had 6 different samples, 3 adult hearts and 3 fetal hearts, and each of those was run as a technical duplicate. And if you then look at the dendrogram at the bottom of it, that's actually, again, quite encouraging that just in a completely non-data-driven analysis, this really pulled it apart very nicely, that we have 2 technical duplicates for each of the samples, that we have 1 class which is our newborn hearts, and 1 class which is our adult hearts, and those two are actually really quite far apart from each other. And when we then look at then we see here at the right end of our heat map the two parts of the two main clusters that really pull the two groups apart. One cluster where the proteins are much higher in the adult heart, and one cluster where they're higher in the fetal heart. And we then, of course, we're also, it's not quite the last slide yet, interested in finding out a bit about what are those proteins. And again, while there were some surprises in there, the ones that really stood out are not that surprising. And if you know a bit about heart physiology, that's what you would expect to see. You notice that as the animal develops from newborn to the adult, the mitochondrial protein, or the number of mitochondrial proteins, really goes up by a lot. And also the myofibrillar proteins that are responsible for the heart muscle contraction go up by a lot. Again, it's not much of a surprise because at the very early, at the newborn stage, that heart hasn't had to work that much yet. Whereas the newborn hearts are absolutely stuffed with ribosomal proteins, which means they're ribosomal proteins are another class that's closely related with ribosomal proteins, is proteins that are involved in translation. So these heart cells are very, very busy to make more protein. It's interesting that whichever approach we took, this was the message that we got out of it. In a way, another factor that sort of supports the idea that it's a good time to buy a mass spectrometer because they're all really very good, very interesting instruments. And this is now really my last slide. It's my acknowledgements to my team at NUPA, which is the Proteomics facility at Newcastle University. One person that I want to highlight in particular is Paweł Palmowski, who is a brilliant postdoc in the lab, who he did his PhD with Ole Jensen in Odense, and really got a fabulous education there. He's dead good. Paweł, together with Rachel, is employed on an MRC program grant that I got with Nick Europe-Finner and Mike Taggart on guinea pigs as model systems for pregnancy, and Julie helped us also with the preparation of the samples. The mass spec data that I showed you were acquired in the demo labs in the UK. Nick Morris used to be probably the best possible proteomics expert in the UK, who's now working as an application scientist for SciEx. Waters, most of the work was done by Francesco Finucara, and Joanne Connolly helped him occasionally, and Jenny Ho, together with Gary Woofenden, did the work